Hello everybody. Today I will present to you our latest work on Strong PUF security metrics, specifically response sensitivity to small challenge perturbations. I'm Rasmus Rasche and I'm a master's student in physics at the LMU. My interests are specifically in information measures, machine learning, and complex systems. The motivation for our work is that currently machine learning attacks on PUF require experience in the field, exhaustive tests to find the right attack models, and access to computational resources. And we ask ourselves if there aren't simpler, easier to apply metrics that could detect vulnerabilities even before machine learning analysis took place. First, I would like to introduce you to the PUF designs that we will look at in this presentation. They all have the same input-output mechanic. We have an n-bit challenge. This will be fed into the PUF, and then we get a 1-bit response. First, we will look at the Arbiter PUF design. The Arbiter PUF consists out of n blocks, one for every challenge bit. We will just focus on the first block for now. We have two signals that come in. Every signal has two paths that it can change. Either they can stay at the same level, which is denoted here with the challenge bit of 0, or they can switch paths, which happens if we apply a challenge bit 1. Each of these paths has a certain delay associated with it. These delays are based on manufacturing variations and cannot be controlled. If we follow the signal path through the PUF, at the end, if we go to this place, one of these signals, either the top one or the bottom one, will be faster than the other and arrive first at the ledge. Which one arrives first determines the output of this PUF. To increase security, k of these Arbiter PUF instances can be run in parallel, as we can see here. All of these instances have unique manufacturing variations, but they all receive the same challenge. After we apply the challenge to them, we also get k output bits from all of the instances, and we then XOR all of them together to retrieve the real output of our PUF. Another Arbiter PUF derivative is called the feed-forward Arbiter PUF. We still have the same stages as with the Arbiter PUF, but now in between two of these stages we can extract the signals already and insert a ledge to already get an output. So we basically check already which signal is first right now. And then with this information we insert at another point, at a later point in the PUF, another stage where we use the output of this previous, basically small Arbiter PUF that we built here, and use this as input for the stage. We can have multiple of these loops, and these loops can also overlap with each other. The last PUF I would like to introduce is the Bistable Ring PUF. This PUF is not built based on the Arbiter PUF, but instead uses a bistable ring of inverters. If we focus at these small elements here, we have these small blocks. We have two elements inside. We can basically think of each of them as an inverter, and the challenge basically chooses which one of these two blocks, which one of these two inverters we use. And then we do this for every block we have, and then we basically have a ring of inverters. Now we can apply power to this structure and just check which state it will have. So if we just say this inverter gets a 1 as an input, it would have to output a 0 here, and then the next one would have to output a 1 since it gets a 0 as an input. And the two stages here are, this one outputs a 0 or 1, and we could basically read out this response at any point in the PUF. Which state of these will be taken when we just switch on the power is based on manufacturing variations. Basically, we can think about one of these inverters being stronger than the other one and forcing its state, so whatever it gets as input, it will also force as an output, and another one will then just react to it. And this will basically determine the state of this. This structure is rotationally symmetric, so we can read out the response at any point here, and this will become relevant later. Now to our metrics. For them, we have n-bit challenges, CI, we have a whole set of them, and we apply them to a PUF instance, and then we get single-bit responses. Now we take the same challenges and flip just the first bit. We apply all of these flip challenges to the PUF as well and retrieve different responses. Now we can calculate a flip probability, call this S, and denote the index with the position where we flipped a bit, so here it's 1. And then we calculate the sum over all of our challenges. The number is S for all of the challenges we have. And then we calculate the difference, the absolute value of the difference between these two responses we have, the flipped one and the not flipped one. And then we also normalize it by dividing it by the amount of challenges that were used. Now we can repeat this for all challenge bits, average over multiple PUF instances. So we can take, for example, 100 instances and calculate the split probability for all of them and take the average. And then we obtain n flip probabilities as 1 to Sn for every bit that we could flip. Now we can look at the results for this. This is for an arbiter PUF. If we look at the x-axis, we have the bit flip position. And at the y-axis, we have the response flip probability. So if we look here at position 30, we could go up and see if we just flip the 30th bit of the challenge, we get around a 0.50% chance of flipping the response bit as well. If we analyze this figure, we can actually see that the arbiter PUF is pretty far away from an optimal PUF. For the optimal PUF, we would expect if we flip any challenge bit, the output should also flip with a 50% chance. This is the dashed line in the middle here. For the arbiter PUF, if we just flip the first challenge bit, the output almost never flips. And if we flip the last challenge bit, the output almost always flips. This actually means that the challenge space for this PUF is smaller than one would expect. We can explain this behavior if we look at the PUF design again. We can see that we start with these two signals, and at the beginning, based on what path they take, some delays are added. But what delays are added here don't really matter in the long run for this PUF. So there's like lots of different stages again, and these could overrule these delays added in the beginning. So it's not decided which of these signals has won yet. And then we have a race through the PUF. And at the end, one of these signals will have won already. One of them will be way ahead of the other one. For now, let's just expect the top one to have won. Now, based on what challenge bit is applied at the end, if we apply a 0, it will go straight through. And if we apply 1, it will cross path. The output is determined. So flipping this last challenge bit will almost always flip also the response bit. But the first stage has very little effect on the output. And this is true in part also for all the stages in between with varying effect, as we have seen in the figure. The real-world security for the arbiter PUF is also very low, which reflects well with our results that we got. Going to an XOR arbiter PUF, we increase the security of the PUF, so we expect our results to get better now. For now, we just look at uneven k, so we have k equals 1, 3, 5, 7, and 9. The green line is our arbiter PUF from before, with k equals 1. And then if we increase k, we can see that the result gets closer to the optimum that we talked about before. So this is in line with the real-world security. Looking at even case, we actually see that the output changes from our test. And the first half is still the same. We start at close to 0 for the flip probability, rise towards 0.5, but then it drops again. Beforehand it would have risen up to around 1. So we have a general bias towards the response not flipping, no matter where we flip the challenge. This can be explained via the design as well. If we focus on the k equals 2 part, we just have two arbiter PUFs that run in parallel. And if we flip the last bit of these arbiter PUFs, both of them have a very high likelihood of also flipping their response. But if we insert these flipped responses into the XOR gate, the output of the XOR will not change because it's invariant under the flip of 2 bits in its arguments. And this also generalizes to higher numbers of even case. If we look at the Forward Arbiter PUF, we still have the same general structure to the curve, so it still starts low and then slowly rises, but we also have these dips and also have peaks. We can explain the peaks by looking at the structure of the feed-forward arbiter PUF again. So after some stages, we will extract the signal and insert it at a later point, basically. So the relevance of these bits, of these challenge bits, of these stages, basically gets increased because they get inserted at a later point in the arbiter PUF again. So by looking at the peaks in this graph, we can actually find the starts of the loops of the feed-forward arbiter PUF, which is nice to see already. So if we analyze the results again, we can see that it is better than the arbiter PUF, but it's still far away from the optimum. And our metric also allows us to start to identify the start of loops. At the inception of this PUF, it was actually resistant against the prevailing machine learning attacks. But if our metric would have been known back then, it would have already revealed its security flaws. Last, we can look at the Bistable Ring PUF, or at the k-XOR Bistable Ring PUF. Now we don't see the rising pattern that we had before, but we have almost horizontal lines. This is due to the rotational symmetry of the Bistable Ring PUF. So we can see that the results are worse than for the arbiter PUF. We can see that there's a very low likelihood of the challenge of the response flipping if we flip just one challenge bit for the Bistable Ring PUF. And the security increase is also slower than for the arbiter PUF if we increase k. We still tend towards the optimum value, so we would suspect that for even higher numbers of k we would get even closer to 0.5. And as I already stated, we can see that the symmetry, the rotational symmetry, can be seen here. Also, this, at least for low k, aligns very well with real-world security, since these low k values of arbiter PUFs have already been broken. Now we come to the second part of the presentation. For now, we've just flipped one bit, but now we will flip 2 bits at the same time in the challenge. We still calculate the flip probability the same way, but now we have 2 indices for the flip probability, one for the first bit that is flipped and one for the second one that is flipped. We will do the same. We repeat over all pairs of challenge bits again. We average over multiple PUF instances again, and then we obtain n-squared flip probabilities. Now we get 3-dimensional graphs. This is the result for an arbiter PUF again. On the x-axis we have the bit flip position j. On the y-axis we have the position m, so we have 2 bit flip positions now. And on the z-axis we have the response flip probability. We can see that this graph is symmetric around the axis where m and j are the same. This is because, and the values are always 0. Here for m equals j, this is because flipping the same bit in a challenge twice will result in the same challenge again. If we analyze this graphic, we can see that the result is similar to the single bit flip result we got. We can see this very well if we just fix m to 0, and then we just look at this edge we can see here, which has the same S-shaped curve as before. But we can also see that that we are still very far away from the optimum, so just flipping 2 bits didn't change anything from the results we got already. But we also see something new. If we flip bits that are close to each other, so for example if we flip bit 30 here and bit 29 here, we see that the flip probability is very low, even though we're flipping like a pretty high number of challenge bit already. And even if we go up to 60, this doesn't change. So it seems like flipping bits close to each other actually cancels out their effect, and it's almost like we have flipped nothing in the challenge at all. This also reduces the size of the effective challenge space a lot. Now we can look at k-XOR arbiter PUFs again. Here we have the case for k equals 2. We can see that the shape curves downwards again for an even number of k, but the same general shape is still visible. For k equals 3, we go closer to the optimum again compared to the normal arbiter PUF, and we also have the normal shape we had from before. But what we also can compare is the slope towards the middle. With increasing k, the slope actually becomes steeper. So this defect that flipping bits close to each other results in very low flip probability gets partly mended by increasing the amount of XORs. What we can also see is that these plateaus at 0.5 are not interrupted by flipping multiple challenge bits. So we still have the same result as from before. They are consistent with our single bit results. And as stated before, the slope to the middle gets steeper with increasing k. Now looking at the feed-forward arbiter PUF, we can see a very complex structure here. We have high peaks again and the dips from before. Analyzing this graphic shows us that the flip probabilities are still very far away from the optimum at 0.5, but it also shows us the strength of our metric. It offers us a very detailed look into what is happening inside the PUF, even though it is such an easy to apply test. If we look at it from the top, we can also see that these slopes to the middle still exist, but the loops partly compensate for them. Last, we can look at the Bistable Ring PUF. It is just a plane at one specific flip probability, just as it was before in the one-dimensional part. What we cannot see here is the slope to the middle that we had with the arbiter PUF, so it seems to be specific to the arbiter PUF. If we increase k, we just increase the flip probability as before, so it gets more secure. To summarize, we have great agreement with our test results with well-known real-world security of the examined PUFs. There are two caveats though. Positive results and good scores are no security proof at all. And negative results, even though they indicate vulnerabilities and show us that future attacks are likely, do not show us what these attacks are and what these vulnerabilities are. They still have to be found, and experts are still needed for this. Our tests can supplement traditional machine learning analysis, and they're also very easy to apply, easy and efficient to apply, and easy to standardize. And now we will also show you how the predictive power of our tests. First example for the feed-forward arbiter PUF, it was introduced in 2004, and it took 6 years to find a machine learning attack that actually broke it. So it was believed secure for 6 years. Our test would have signaled the vulnerabilities earlier on. And last, we would like to make a conjecture. Our test shows that the Bistable Ring PUF seems worse in security than the arbiter PUF, the k-XOR arbiter PUF. So we conject that the k-XOR Bistable Ring PUF with k larger than 4 should be broken in the near future. Let's see, everybody. We'd also like to thank the AFOSR, which has supported our work. And with this, I end. Thank you for your attention. If there are any questions, I would like to have them. You can also always write me an email.